Okay, students, welcome back. We will start with the next session on our Transducers Engineering Unit number 2. Previous class, we were looking into the different types of temperature measurement using the resistance transducers, and we are into the resistance transducers, and we are looking into different kinds of parameters measurement. First, we saw the displacement measurement, the linear displacement, angular displacement using potentiometers, these things. And next we saw about the measurement of temperature. We are looking now using the different kinds of temperature transducers such as RTD, which is the resistance temperature detector, and the thermistor, which deals with the principle of increase in resistance when there is going to be a temperature change with respect to resistance change, that is called as the temperature coefficient of resistance. And also we have been included in the syllabus on thermocouples. So I also explained you in brief about how the thermocouple works on the principle of Seebeck effect. To have a rehearsal of what we have seen in the previous class, I just start with the Seebeck effect. Seebeck effect. Today we will see in elaborate, and also I will show you a practical demonstration to measure the room temperature today using the thermocouple. As we have seen, the Seebeck effect defines when two dissimilar metals, let us take this is a wire, this is a dissimilar metal, and this is a different metal. When they are joined together only at their end, they are joined together only at their end. Okay, let us take this joining as J1 and J2, junctions of J1 and J2, and they are maintained at the temperatures of T1 and T2. T1 and T2. This T1 is not equal to T2. Okay, and that is so, hence this T1 and T2 are in a temperature gradient. Okay, either the temperature T1 can be greater than T2, and or the T2 is greater than T1. Okay, let us take T1 is greater than T2. T1 is greater than T2. So this is called as a hot junction, and this is called as the cold junction. Okay, so T1 is hot and this is cold, and this junction or the hot junction is the one where we are going to insert this junction inside a parameter measuring environment. Let it be a water bath or a room or a gaseous environment or even a molten ion, whatever may be the case, we can even insert this end to that area and then we can measure the temperature. Okay, so hence it is called as a hot junction and the other end is called as a cold junction. Okay, here when this kind of an inequality or a gradient occurs in the temperature at these junctions, then naturally a phenomenon of an EMF generation occurs. Naturally an EMF is generated here, okay, from the two wires. We take this EMF and then that EMF, which is the voltage, is proportional to this gradient of T1, which is not equal to T2. This voltage generated, okay, is proportional to T1 and T2. This voltage generated is proportional to this temperature gradient. So this, hence the thermocouple, you have to recall, this is an active transducer because it produces voltage itself by the phenomenon or the physical parameter that is being changed. Okay, it directly produces an voltage and we can take this voltage which is proportional to the temperature change or the physical phenomenon what is being occurred. So we can take this one and then compare it with a piezoelectric sensor which gives a electrical output with change of mechanical stress. Like that, here you are going to give a change in temperature and you are able to get the electrical output. Hence it is this thermocouple is an active transducer. Okay, a thermocouple works on the principle of Seebeck effect, and it's an active transducer because it produces an voltage without an external any kind of bridging circuits or any electronic circuit, and you're able to get directly the output voltage from this. Okay, so this is the main advantage or a criterion that we see in thermocouples. So there are many different kinds of thermocouple like J type, K type, okay, S type, like this it goes on till around 12 to 17 types of thermocouple based upon the principle of its material variation. Okay, there are different kinds of copper constantan is J type. Okay, nickel chromium comma nickel alumel, okay, combination is K type. Okay, so like this there are several different kinds of combination which are having different kinds of properties to measure, like the J type can measure 0 to 800 degrees centigrade. This one can measure from minus 50 to 1200 degrees centigrade. Like this, depending upon its material property, you will be able to have different kinds of ranges and different kinds of material properties, and you will be able to measure and go for different kinds of applications. So this is the main advantage of a thermocouple, that it has a very different kinds of thermocouples can be produced by this method, and it can be implemented for measuring the temperature. Okay, and thermocouples are the most commonly used temperature measuring transducers in industry. Okay, and there are several more in-depth topics in thermocouple like cold junction compensation, and all these things will be explained to you in the next semester or the next subject named industrial instrumentation, where you will have a separate topic on thermocouples alone. Okay, and there we will have a detailed discussion. Now we will go for a practical demonstration on thermocouples using a K-type thermocouple. Okay, here I have a K-type thermocouple with me, which is nickel chromium one wire, and the other wire is nickel alumel combination. Here with this multimeter I have attached, okay, a K-type thermocouple. See here this wire is a combination of two insulated wires, okay, and the edge of the wire is joined together. The edge of the wire is joined together exactly here. You see that two insulated separately, they are just joined at the junction, and this is our hot junction. Okay, so what I have here is a outside you have a sheath which is a protective covering. Inside you have two wires which are insulated, and just at the junction they are being soldered, and you see here at this junction it's a soldered junction. Okay, so when you expose this junction, this is the hot junction, outside to the room temperature, you should be able to measure the room temperature. Okay, now I have inserted the cold junction at the other end to the multimeter, and inside it has all its signal conditioning units. Since now I go to the temperature measuring section. Yes, it's perfectly displaying the room temperature. 27.0 is being displayed. This is the room temperature what you have now inside this room, and it is 27.0 is the room temperature. If you want to compare and see, you have to take a laboratory thermometer. As I told you in the first unit, you have to take 10 readings for every 2 minutes, and then whether you have having what kind of an error, everything can be calculated, whether it is going to be a linear combination, everything can be checked using this single sensor. Using the, we have also our, you can very well see the temperature is also getting reduced. Let us see here. Now it is getting reduced. I am going to touch this end and it should increase because my hand is little hot. See here, so it's very well increased because my hand is hot, because my body temperature is around 37 and maybe my hand finger temperature is around 32, so exactly it is showing 32. Okay, so this is the thermocouple where you have the junction and then it is used for measuring the temperature. Now you see that it has been reduced, so it's a very sensitive temperature sensor which can be used for measuring different kinds of applications in the range of around 0 to 800 degrees centigrade. This can be even now introduced into a furnace and where you can take the readings from this multimeter directly. Okay, so I hope that you are very clear with this thermocouple concept. We will now switch to a very different, very interesting sensor. Now let us go inside the discussion of a broad topic named strain gauges. Okay, strain gauges. What is strain gauges? Why we need strain gauges? To measure stress or strain of a material. This was called as strain gauges. These strain gauges, why we need this? Because when you apply any force to a area or some metal or any kind of plastic or wherever, you need to measure force, weight, pressure, strain, torque. Okay, all these things cannot be directly measured by seeing your vision or something like your direct sense. Then you need a sensor which you can measure using this kind of a sensor. Here we come in across this strain gauges. Okay, before we enter the strain gauges in detail about as a sensor level, I will explain a basic some physics principles. Okay, now let's take a wire. Let us consider this is a wire AB. It has the length of 10 centimeter. Okay, it has a length of 10 centimeter. So this is the length 1. It has a length of 10 centimeter. Okay, then it is a wire made of copper. Okay, and it is has a dimension of 1 millimeter diameter, 1 millimeter diameter, and it is length is 10 centimeter. Okay, you have fixed this wire to some pins. It is in a stretched manner, it is fixed. Okay, in some stretched manner it is, you have fixed it is 10 centimeter wire. Okay, then what we do, we measure the resistance of this wire. Let us imagine we are getting 20 ohm. Okay, then what we do, we have fixed this one to the pins and we apply a stress or a force of 5 newtons to this, just this length of wire. We are applying a force. This length of force, what it does, it makes the wire to bend. Okay, it makes the wire to bend. Why this bending occurs? Can you bend? Imagine here we have a metallic wire or a plastic wire, it can bend. Okay, can a rigid ceramic or a glass rod of 10 centimeter length can bend? No, it can't bend because there is no elongation occurring there in the glass rod. Okay, here it is able to bend just because of the reason that it has become elongated. That is the one single reason it's able to bend, and it is able to withhold the force that is being applied over here. If you apply a severe force over a material which is cannot bend or extend itself or elongate itself, it will break. Okay, here there is a bending action occurring and it is malleable and ductile. This condition of malleability and ductility is suitable mainly for our metals, and it also has the conductive property. Hence we are selecting metallic wires for strain gauges. And now we are coming back to the point. Here we are using a metallic wire and we are applying a force. Okay, and it has bent. This bend is occurring because of an elongation delta L. Okay, this delta L combined with L1 gives this L2. Okay, it's true. Then the strain which is caused because of this 5 newtons of force can be calculated by L2 minus L1 divided by L1. This is the strain. Okay, so this is the basic principle behind strain gauges. Apart from this, I told you it is a copper wire. Yeah, this copper wire, every material has a property of resistivity. Resistivity is the property to resist the flow of electrons or current. Okay, that is resistivity. This is given by the constant rho. Depending upon the resistivity, the resistance of the material for a given amount of length and the current flow will change. Hence, the basic equation for strain gauge, the resistance of the given length, given area, that is 1 millimeter, okay, and 10 centimeter will be rho L by A. This comes from this because the resistance is proportional to length by area. Then this proportionality is removed by introduction of this constant of resistivity, because resistivity comes from each material because it is dependent. Hence we introduce this rho. Rho is resistivity of a material. L is the length of the material. A is the cross-sectional area. Of the material. Hence, this resistance before the application of force will be 1. Let us take it as R1. Okay. After application of force, okay, the length varies and also the area varies like this. The length increases when the length, imagine an elastic band, okay, and if you are going to stretch the elastic band, the length will increase. If length needs to be increased, the area of cross section has to decrease, then only the length can increase. So only it has come to the inversely proportional mode and length has become the directly proportional mode. Hence the ratio R1 equal to rho L by A comes into picture. Okay. So this is the base equation of any strain gauge. The resistance is equal to rho L by A. Apart from this, we have one main feature called as gauge factor. Everyone has to remember this gauge factor. Gauge factor of any strain gauge, okay, is something like this. The gauge factor or GF equal to R1 by R2, which is R1 is the before change, R2 is the resistance after change divided by strain. This is a simple equation by which how much strain a single strain gauge can withstand can be calculated. This is called as gauge factor. Okay, this gauge factor is a commercially very important parameter by which you can select strain gauges for different kinds of applications. Now so we will see some practical examples regarding strain gauges. First I will just introduce you to a strain gauge. There are different kinds of strain gauges. We will go into details of what are the types of strain gauges now. Before that, I will just introduce you. Can you see here? There are two ends. Inside this, there are minute, very minute, within millimeter lengths of wire. Okay, embedded are just packed between, sandwiched between two foils. Okay, metallic wire sandwiched between two foils, and just the end is being given to you as two wires. This kind of a strain gauge, which is having metal embedded between two layers of polymer, are called as metal foiled strain gauges. And these are unbonded. Okay, first let us take the types now. Types of strain gauges: bonded, unbonded. Okay, types bonded and unbonded. In the bonded type of strain gauges, how it looks is, it simply as it works how raw. Totally it works in a raw fashion. You have a wire which is wound over a stack, something like this. It has 4 columns which is wound over this stack. Okay, and you have a platform for application of force. Okay, this force will make it to elongate. Okay, simply it will make it to elongate the entire wire which is wound over here, and this elongation can be measured, and you will be able to calculate the stress by the calibration. This is a very old fashioned strain gauge, and all the new strain gauges are this metal foiled strain gauges, and then sandwich strain gauges and polymer based strain gauges has come into picture. Okay, and these are this kind of strain gauges where we have this same principle. It is like this: there is a metal, okay, but it is to increase the sensitivity, the entire thing, the length of the wire is bound in this fashion, and you get like this, and you can measure the resistance over here, and this is put up inside a polymer sheet. This is what you see here inside the small sheet. Okay, this is unbonded strain gauges. So this one only we are going to see now. Okay, so I have now introduced you to a single element of a strain gauge, an unbonded strain gauge, which will be used for measuring several different kinds of applications, something like force, pressure, torque, etc. Okay, so there are different kinds of applications for the single these are called as primary sensing elements. Using the single small primary sensing element, you can build different kinds of big sensors, and you will be able to measure different kinds of parameters. So these parameters are force, pressure, torque, etc. We will now see this. We are seeing about the strain gauges. This is a single element, as I told you, and using these strain gauges we are able to build different kinds of second level sensors or transducers. These will act as secondary sensors, and the whole setup will be called as a primary transducer. Now we are coming to the concept of primary transducer and secondary transducer. Okay, what is a primary transducer and a secondary transducer? This is a major definition or a difference that occurs in transducers. The primary transducer is a transducer section or the element where the direct physical phenomenon is going to act over that. Okay, but this can't directly sense the physical phenomenon. There is inside a primary sensing element present which is going to act or take this physical parameter and sense and give the output. Okay, so the entire setup is called as the primary transducer, and the real primary sensing element which is present inside this entire setup is called as secondary transducer. Okay, so this is the major thing. So here you have the primary sensing element. I have it for you here. Okay, now I am going to show you the primary sensing element. Here I have showed you. I will show you now the primary transducer, which is a load cell. Okay, load cell, which is called as a primary transducer because see here, it is the load cell. This is a load cell. In an actual arrangement, you have to imagine this as a cantilever beam. Okay, this is a cantilever. Typically, it's a cantilever beam. Okay, and this is a typical cantilever beam, and we are fixing like this. And here we will be applying the force or a load. It will be applied. You can very well see here there are several primary sensing elements or strain gauges fixed over to the load cell. This entire setup is called as a load cell, and inside the load cell they will be covering all these places with polythene or polymer materials, and nothing of this primary sensing elements will be visible to the human eye. And I have just removed it for the demonstration purpose. You are seeing here, here is one primary sensing element, the strain gauge, and here is one, and here is two, and here you have another two and another two here. So there are four over here, four over here. This is called as a full bridge, and here it is called as the full bridge circuit. Now, I will now measure and show you the resistance for each strain gauge which is present. See the resistance now, what's being measured. Can you see here? I am measuring a resistance for a single strain gauge. It is 350 ohms. Okay, it is 350 ohms. 350 ohms. For another one sensor, that's also 350 ohms. Again for another one 350 ohms. Like this, inside this load cell they have utilized all the primary sensing elements or the strain gauges as 350 ohm transducers. Here it has been utilized, and they have constructed a full bridge circuit. The full bridge circuit, what is this full bridge circuit? Inside a Wheatstone's bridge, okay, you have to recall a Wheatstone's bridge, and inside a Wheatstone's bridge, everywhere in each arm, one single primary sensing element is being connected, and the output has been taken. Okay, so now you have been exposed to the load cell. This is a load cell for measuring weight. In your laboratory, you will be having this kind of an experiments to measure weight from the load cell, and from the load cell you will be able to get the output weight. We will be calibrating the voltage that we get from the Wheatstone's bridge, and that will be calibrated to weight. We will be directly measuring the weight out of the load cell because the voltage is calibrated to weight. Now let's come back. how we are able to measure this strain gauge resistance. The strain gauge now is connected to a Wheatstone's bridge circuit. Yep, true. So let us take this is P, this is Q, R and S. These are the different resistances what we have here, and as per the normal rule we will be having P by Q equal to R by S. Here the unknown variable comes from the strain gauge, and so P equal to RQ by, using this equation we will be able to get the strain gauge value. Okay, so now we have been exposed to what is a strain gauge and how using strain gauges we will be able to build the primary transducers or the load cells to measure force, and using the same way we can also measure torque. Okay, from the next class we will be exposed to some more transducers for using the resistance phenomenon, and we will be closing the unit 2. Thank you.